Welcome to the ACOM seminar. It's my pleasure to introduce today's speaker, Dr. Jeff Anderson. Dr. Anderson has advanced degrees in software engineering from UC Berkeley and geophysical fluid dynamics from Princeton University. After a postdoc at the National Centers for Environmental Prediction, he led experimental prediction and model development groups at NOAA's GFDL. He came to NCAR in 2001 and has led the development of the data assimilation research testbed since 2003. He's a fellow of both AMS and AGU. So before I start, I want to remind people watching online that you can enter your questions in the space below the video. And after the presentation, I will read the question to Dr. Anderson. And let's welcome Dr. Anderson.
Okay, so it's a pleasure to be back in what is now called ACOM. The last time I gave a seminar here was in 2007, so 16 years. That's way too long, but we've been thinking really hard about good reasons for you to want us to come back, and I think we have some in what I'm going to talk about today. So during the pandemic, our team, which is up at the Mesa Lab in CISL, we developed data assimilation tools, something called the Data Assimilation Research Testbed, an Ensemble facility, and we've been really keen in on some new capabilities that are engineered specifically for a lot of the problems that come up in chemical weather prediction, chemistry of the atmosphere in other ways, things with tracers and all. I'm going to tell you a little bit about that today. I've rebranded as much as I can, by the way. I understand that we have to have NSF in front of NCAR, and the NSF logo is supposed to be on the left. I couldn't actually manage to do that yet, but at least it's on the right. Cool. So data assimilation, a quick review for a few of you who may not know exactly what it is. Data assimilation takes prediction models, maybe CAM-Chem, WRF-Chem. It takes an observing system, maybe satellites, ground-based measurements, aircraft measurements. It gets forecasts from the prediction model. It gets observations from the observing system. And data assimilation is a statistical technique that combines those things. It produces something that's called normally in atmospheric fields and analysis might be called a posterior to, which is the combination of these things. It gives you a state of your model that is hopefully more accurate than the original one and also contains these informations from the observations. It can also provide you a whole bunch of diagnostics about how things are going on. And normally, in the context of things like numerical weather prediction, this is a cyclic process. So we get an analysis by combining prediction model and observations this morning. We then use that analysis to make a forecast to, say, this afternoon, where we do the whole thing over again with new observations, and it just keeps rolling on forever. Now, there's a lot of other things one can do with this besides just making forecasts, which is what numerical weather folks do. You can identify systematic errors by confronting observations with the model. This can improve your model. It can also just tell you that there are problems with your model. It may be a lot of work to figure out what those problems are, but you know that they're there. You can directly estimate model-free parameters with data assimilation, treating them as a variable. In particular, for applications I'll talk about today, in many chemical model simulations, the concentrations of tracers are really prescribed. They're actually more a model parameter than they are what we would call a state variable. But this same capability allows us to estimate those sources and potentially sinks. In the same way, you can also use this confrontation between model and observations to learn more about the observing system. You can estimate the impacts of particular observation types. You can actually design systems. You can ask questions about, if I put an instrument in here that looks like this, if I lofted this satellite, what would it enable me to learn about the state of chemistry in the atmosphere? Okay, and it's all about Bayes' theorem. I'm not going to go... I'm a graphical thinker that's forced to do math on the side, and you'll see that come out in this talk. There's going to be a lot of graphical thinking and very few equations. This is the key one. So this is a form of Bayes' theorem. It is the crux of all data assimilation that's done in geosciences. So basically, the green term on the numerator over there, that is the prior. It's the forecast from the model, and they give you a probability distribution. Everything here is about probability. And that's what the green term is. Similarly, from the observing system, you get something that's actually called a likelihood. It's the probability you would have observed what you did observe, given the state of the model. That's the red term. And you just multiply these two things together. It's because it's an and you remember your basic probability. Ors are adding, ands are multiplying probability. And so on the left, we get this analysis or posterior, the probability of the state of the model given these new observations. And there's this really ugly denominator down here. One of the beauties of ensemble methods is that I can just ignore that denominator. And people who do ensembles basically forget that that ugly term is even there after a while. But, oh, it's nasty. Okay. So, a quick overview of DART. So it is state-of-the-art, designed specifically for ensemble data assimilation for geoscience, although we have other application users. DART can be used for something called ACOM, Observing Simulation System Experiments, and that's where you say, I don't have these observations yet. I don't have maybe a model of the real world, but I want to combine a model and observations and see what I can learn about what those observations do. And so this can be used for designing observing systems before they're ever built. But DART can also be used and is frequently used for real assimilation, basically for numerical weather predictions analogy in many, many different parts of the Earth system. Okay, it can make analyses and forecasts, compute the value of observations in the real world, and tell you things about parameters, sources, and sinks. We'll see examples of this later on. So since we're at NCAR, DART specifically is designed to run well on NCAR supercomputing. It runs on many, many other supercomputing platforms too. It runs on the largest applications that anyone at NCAR can afford to run. And so the limitation is, can you get enough time to do that? We can run on whatever the biggest thing you can get. And the software is very carefully documented. Surprisingly, our biggest problem at the point right now is we have too much documentation. You don't see that in science very often, so we need to get it more focused down again. And we have support by our team, so we provide user support both within NCAR, and you'll see some comments on that, but also with UCAR community scientists. Okay, so DART is a framework. It is a system of tools to do ensemble data assimilation. It's very carefully engineered to make it relatively easy to use new models. At present, there's about 4 dozen large geoscience models that have been interfaced to DART. Currently, about 2 dozen of those interfaces are up to the current version and are actively used, but other ones can be brought back up to date. You can see many NCAR models on here, many models that aren't from NCAR 2. I've highlighted a few. In particular, we'll see stuff from CAM-Chem and WRF-Chem today. We also work with MPAS Atmosphere, and we could work with MPAS SEMA if anyone wanted to do it. Higher models like WACOM-X or WACOM, TIGCM, which is also used, and the land surface models to go underneath this if you need it, or the ocean models underneath it too. So lots and lots of NCAR models fully supported. We also try to support NCAR strategic projects. As an example, since there's leadership of this project coming out of ACOM, I wanted to stress it. We've been supporting SEMA. DART currently works already with most of the SEMA primary dynamical models here, so all those ones that are listed up there. DART will also work with Musica version 1, which is in essence still CAM-Chem out of the box. We do not anticipate serious difficulties in implementing DART interfaces to later Musica versions, so mechanistically simple. Science is still a hard thing, which is why I'm here talking to scientists. Okay? Another key part of using an ensemble data assimilation or any data assimilation system is things called forward operators. These are pieces of software that take what your model tells you and say what you would expect an instrument to observe. So if you give me a CAM-Chem state vector, so all the temperatures, concentrations, and everything else, a forward operator would then say, okay, I have a retrieval of CO, and I'm going to get it wrong. Tropomi? Can I get CO from Tropomi?
Yes.
Yay, I got it right. So I want to get a column retrieval of CO from Tropomi. And so this would be a piece of software that converts from the model state and says, this is what I think you would see with the instrument. You will see that there's been lots and lots of work with forward operators for chemical applications going on with DART. Some of it started here in ACOM and moved out to other places too. It is straightforward in DART again to implement these things, to add in new observation operators. Getting the science right once you do that can be more challenging. And I'll pretty quickly skip over this slide. We work with lots and lots and lots of different types of observations, but I'm going to key in on some specific chemical ones in just a moment. So we've been doing this for a long time. I said I last talked here back in, I think, 2007. I'm going to quickly show you some projects that were done by graduate students in the early 2010s. Both of them were finished in 2015, just to tell you that, yeah, we have some experience doing this. This particular project, which I won't give details with, was using CAM, a sort of pre-CAM-Chem version. The graduate student of Inez Fung's at Berkeley, Stephanie Worth, and basically she used CAM to estimate the sources of CO2 at the 1 degree or 2 degree model grid scale, and she compared those to other things, common products of those, carbon tracker, declared sources. She in particular was interested in, could you detect if a particular large country was misestimating their outputs by a factor of 2? And at that point, there were countries where you could certainly detect that with this capability. Another early example, again, you'll see some folks that were in ACOM at that point, Arthur Mitzi leading it. Shuling Liu was a student of Inez and Ron Cohen's at Berkeley. This is a different scale. This was done with WRF-Chem at an extremely fine scale. Some of you, if you actually imagine it, this is actually the Denver metro area in these plots. You can see, I'm going to walk away. I know there's people online, but you can see down to the south here. Okay, that's I-25. You can see Suncor up there. You can see the downtown. You can see a little bit of 36 heading off to Boulder. These are now NO2, as I said, done in a very high resolution WRF-Chem model and assimilating observations from a variety of sources. These particular examples are from these ACOMs that I've described to you. They're saying if we had these observations, could we, as an example, detect violations at Suncor? The answer, of course, I can't say this online, is you can probably detect violations at Suncor without any technology at all. Okay, now I want to go to some more recent work. I'm going to really quickly go through this because the folks leading this work could give you a beautiful whole seminar or multiple seminars on this. These are some slides I got from Arthur Mitzi, who's been using WRF-Chem with DART now for well over a decade. He has collaborators all over the place at NASA, NOAA, University of Colorado. Quickly, again, I'm not going to go into all the details of this because I want to tell you about the data assimilation part, but there's lots of science here. Here's a list in the second bullet point of the different types of observations that Arthur's been actively assimilating. So you can see many of your favorite instruments, Mopediazi, Modis, Tropomi up there, Siamaki, which I can never pronounce, Tempo, and then different chemical species. In this case, mostly retrievals is what Arthur's been working with, that he's been assimilating. You can also see them continuing to work on new types of observations. Those require forward operator development. And in fact, Arthur's research has primarily been on the development of more accurate forward operators for satellite retrieved concentration observations. He does lots of other stuff too. Again, I'm not going to go through these slides in details, but things that he's been working on with WRF-Chem, the second bullet point is joint assimilation, so assimilating not only weather obs, but observations of different species from different satellites at the same time. There's lots of interesting applications, so I think you know many of the common ones, but another example of these things, we're using COVID as a scientific win, looking at the difference in different emission years, looking at different observations that are coming forward. I'll show you quickly a slide from some wildfire applications. Greenhouse gas I know can be of less interest to active chemists, but there's work going on there too. Lots and lots of interesting work going on with air quality forecasting. Again, basically chemical numerical weather prediction. This is just one slide to show an example of some of the work he's been doing. In this case, assimilating OMI NO2, total tropospheric columns. These are for cases with an active wildfire, looking at the smoke. Now you can see that there's lots of good things happening here. It also shows you how much more work there is to do. So this is state-of-the-art stuff. You can see the observations on the left. You can see a case where there's not assimilation of the NO2 observations in the middle, and then the impact of assimilating those. You get rid of a lot of these false things coming out of the models. You see a lot of the fire plumes too. There's still other stuff going on there, so there's work to do, but this is definitely an example of the type of great progress you can make assimilating these things. Okay, another example of collaborations, these ones are with CAM-Chem. These are led by Ben Gobert, but I think there's some people in the room who are working on this, many people from ACOM and their collaborators. These are examples at 1 degree, global models, and assimilating, in this case, CO from Chris and Moppet. And again, this is work that's being done here, so I'm not going to spend too much time telling you the details. Ben can do that any day. But basically, he's done a number of different cases, some where there is no assimilation, then some where he assimilates Moppet observations, one where he assimilates Chris and Moppet, and then there's some algorithmic exploration. I'll get back to later. But basically, this is focusing on China here. You can see over here he's plotted the differences between a background field. So these are RMSEs to a ground truth. You can see the top panel A over there, the middle top one, is with no assimilation from these sources. Then you do Moppet in the top, Chris and Moppet in the lower left, and we'll come back to what the other panel is. But this shows the capability. He's able to run these things for extended periods of time and use these observations effectively. Okay, background. Now I'm going to change to the cool new stuff we can offer you for chemical assimilation applications. So you all know the MESA lab. So I work at the MESA lab. I get around exclusively by bicycle, and so I have more than 4,200 round trips since 2001 up and down the Mesa Road. Okay, so sometimes that's really nice, and sometimes it may not be as nice, so there's some weather issues. And so I'm going to talk to you in an idealized sense now about how data assimilation can help me stay alive and healthy with this commute. So you're going to see this plot a lot in the next few figures. So I'm going to say I have 10 forecasts of the temperature at the Mesa lab, and those are shown by the green dashes up there on the top. They're all just a little bit above zero. And then I have an observation. Unfortunately, this week the mast on the Mesa lab is down while they're redoing the roof, but I have an observation of the temperature, and that might be the red asterisk here, just a little bit above zero, but then there's some uncertainty associated with that observation. My real question is, do I need to go 40, okay, 35, that's the speed limit, 35 down the hill, or should I be going 10 down the hill because there might be ice out there? So this is how historically ensemble data assimilation has worked. We fit a normal distribution to the model prior for this observed variable, and there it is. Okay, so it has a mean, again, probably about 1c, but there's a tail out here. And then I use Bayes' formula, which tells me I need to multiply this probability distribution from my model, the green one, with the probability distribution from my observation, the red one. And if I multiply that, it's done pointwise for each value of the temperature, I get the blue curve down below. So that's my analysis distribution of the temperature. Now I have to do some sort of magic to get an ensemble that's consistent with that posterior, and I'll talk about that part of the algorithm in a moment. And in this particular case, you can see down at the bottom, I end up with 3 ensemble members that are below zero. And so maybe I'm saying, okay, there's a chance, it's not great, but there's a chance that there's ice on the hill, so I should be careful. Now, I'm never going to change the green ensemble members or the red observation value in the slides that follow. And so the next slide, I'm literally just going to change the axis label. Okay, so instead of temperature, it's now ozone times 1,000 ppb or something like that. It's just ozone concentration. And that might be relevant. There's the NCAR fire burning there. I use this to tell people outside of NCAR that there's some days with bad air quality here. So now I'm going to do exactly the same thing I did before. So these slides are identical to what I showed you for temperature. Okay, and so there's the posterior. And it has 3 ensemble members that say the ozone's going to be negative. Okay, well that's not my first choice here. Ozone's not going to get negative. How am I going to put those back into the model? At best, maybe I'm going to say, okay, well, there's 0 or something like that, but that's certainly messing up my statistics here. And so historically, we have been stuck at this point, what to do about bounded quantities, which come up some for tracers that you look at, but come up even more for sources of these tracers. Okay, so it turns out now that what we can do, what Dart now offers, is we can fit any distribution to the information we get from the model, and we can take any distribution that the instrument developers give us about the error associated with the observation. And so here's just an example for this particular problem. The red asterisk and the greens are still the same, and instead I fitted a gamma distribution here. The gamma is bounded below at 0, so it says I can't have any negative ozone. And I take this product, which we can do, and I get an analysis distribution in blue, and I fit ensemble members to it, and okay, they're not negative. Okay, I could provide you more evidence that they're actually sort of the right thing if this gamma is the right distribution. Okay? And as an aside, collaborations. There's a lot of instrumentalists down here. Instrumentalists have traditionally not had a market for things that are past a sort of plus or minus this error on your observations. I mean, a lot of you realize, of course, that a measurement of negative is ridiculous, but there hasn't been a market for this. And so there's a lot of room for collaboration with folks who have instruments who actually know more about the error characteristics of that than plus or minus 1. And we're really interested in looking for collaborations with people who have things like that. The other thing I'm going to quickly tell you is the secret to this is actually really, really simple. I've been trying to solve this problem since 1997, and when I finally figured it out in the middle of the pandemic, it was like, wow, you are not very smart, because any undergraduate student thinking about this problem should have figured this out. So the solution is trivial, and here's the story. In that upper green distribution, each one of the ensemble members has a quantile. For those of you who aren't used to quantiles anymore, it's sort of the same notion as a percentile. So the one on the left here has a quantile of 0.42. It means that there is a 42% chance that that green distribution is less than it, and a 58% chance that the green distribution is more than it. Similarly, there's one that's 0.87 there towards the right end of that. It says that most of the probability is less than it. And literally, all we do is take those quantiles and fit them down in the other thing. And so now the fifth highest ensemble member in the posterior also still has a 0.42 quantile associated with it. And so you can do this with any distribution now. Again, once you see this, there are theoretical reasons to believe this is a good thing to do. I'm not going to try and motivate them more today. What I am going to say is this. Maybe it's obvious that a gamma is a good choice here. Maybe it's not so obvious. Okay? I don't actually know what the distribution is. And so we have a lot of quantities in atmospheric models and chemistry models where we say, I'm not quite sure what distribution I should use. And so DART provides something called a non-parametric distribution, a bounded normal rank histogram distribution, which actually just uses the ensemble members directly to get a PDF. You can see an example of that probability distribution function in the green up there. It looks funky, okay? However, it has lots of really nice statistical properties. In this particular case, I can again multiply it with Bayes. I get a blue that now looks like this type of distribution, and I can fit the ensemble members in the same way. It turns out this is super powerful, and with moderate size ensembles, it's almost as good as if you know the distribution. If you really know the distribution, if you really know it's normal, if you really know it's gamma, you're better to use that information. If you're just saying, oh, well, maybe it's kind of approximately gamma, you may be better with this. And all the examples I'm going to show from here on out, with the exception of some of the figures of bends I'll go back to, are actually done with this distribution. So a user didn't have to make any choices at all except to say, I don't know anything, so I'll use this default. Okay, and I don't want to go into the details here, but basically what this distribution does is if you have this ensemble, here's an example of 5 ensemble members at the bottom. They partition the real line into 6 intervals. Okay? 2 external ones and 4 interior ones. And what this distribution type does is it puts 1/6 of the probability into each one of these intervals. It basically says, I don't know much about this ensemble distribution except that it looks like a random draw, so that each one should be sort of 1 over n plus 1 of the way up the distribution. Okay, some of those figures were done recently. This was the very first set of figures that we ever did when we rolled DART out the door in 2003. So some things never change if you make good decisions early. This is a schematic of how the ensemble data assimilation algorithms in DART work. So at some time, say this morning, T sub k, we have a set of ensembles represented by blue asterisks. It's the CAM-Chem model state. So each asterisk is this huge long string of temperatures, winds, and concentrations in the model. And we make a forecast up to this afternoon when we're going to do assimilation time tk plus 1. DART is completely sequential. It just does one observation at a time, whether you have 1 or 10 million this afternoon available. So it takes the first observation and it computes the forward operator. That's the H's here. Maybe that forward operator is getting the Tropomi NO column over Boulder. And so I get, in this case, 3 estimates from the model of what that instrument would have observed. They're shown in green on this top scalar y-axis. I then get the information from the instrumentalists. They say, well, here's the observation in red, and here's our best estimate of the error distribution. Originally, this had to be normal. We then do this stuff that I just talked about, this one-dimensional problem for what's going on at the Mesa lab. We now do it for this Tropomi observation. And we get increments for the Tropomi observation and an updated estimation of what that observation is. Okay, that's all swell, but I really care about my model state. I want to update the variables in CAM-Chem. And DART also does that in a serial fashion. What it does is it takes the ensemble distribution of, say, the gridded temperature over Boulder at 700 hectopascals this morning. That's from the model. It takes the prior ensemble of this tropomi observation, which was computed by the H's, and so it gets a bunch of little dots from that, and it literally does a linear regression of these increments. I'll show you a picture of this in a minute. And then it does all the other observations like that, one at a time, looping around. They can all be done in parallel, it turns out, which makes it start fast, and then you move on to the next time. Now, the stuff I showed you on the Mesa Hill is this top part. It's this scalar problem for an observed variable. And at this point now, we have a nearly general solution for that. You can literally use any distribution you want. You can use any assumptions about that distribution. And that's what I gave you a little bit of flavor for. That's great. Unfortunately, the second you move to this regression step, and you take those increments for the observation, and you try to use them to update, say, the gridded temperature in CAM-Chem, all bets are off. Now, I'll show you an example of what that looks like. And it's kind of disappointing when you say, oh, I can do all this great stuff for observations. So again, this is an idealized case. The horizontal axis is an observed temperature, again, let's say at the Mesa lab this morning. The vertical axis is an unobserved variable. In this case, maybe it's the ozone concentration at a grid point near the Mesa lab. And I've just put on there 100 ensemble members in green asterisks. So these are things that came from a model forecast and maybe this forward operator. The temperature is probably pretty well normally distributed in the free troposphere. And what we're going to do is we have the red curve shows an observation for the temperature. So the temperature is observed, and the observed value is a little bit less than -1. And so the first thing we're going to do is just for the horizontal variable, the temperature, we're going to do that stuff I talked about a minute ago. But then we're going to regress those increments to try and find how to change the estimate of the unobserved quantity, the ozone. And what we get are the blue asterisks. The gray shading underneath is actually the correct solution in this case, computed by a very expensive offline computation that you could not regularly do. And so we see the temperature thing has worked fine, so the horizontal values aren't bad, but the values of the ozone are just a mess. There's a bunch of them that are negative again. There's a bunch of them that are far outside of the distribution. So, gee, I'm really disappointed. I did all this hard work on the observation space. So we have to fix this problem too. Let me show you why this problem occurs. This figure actually has the same green asterisks as in the left panel here. I've just removed the shading. And what I'm going to do here is I'm going to show how this regression works. So I've computed increments for the horizontal variable, the temperature. That's the algorithm I talked about a moment before. And I'm going to just take a least squares fit, shown in the dashed line here through these 100 green asterisks. And then I've just highlighted 10 of the prior ensemble members. Their change in the horizontal direction was determined by what we did with the temperature. Their change for the ozone direction is determined by this change has to be parallel to that least squares line. And so you can see for these 10, they're all moving generally towards colder temperatures because the temperature ob was less, and they're moving to lower ozone concentration because there's a moderate positive correlation. But they don't know anything about the fact that ozone is bounded, so you can see in this case 5 or 6 of them go negative. And there's some up there where there's some curvature, and again, since you came, you deserve to see the hand waving. So you can see some curvature here, and you can see that it doesn't know anything about that curvature, and so you're getting stuff above the distribution. So this is unhappy. We're going to solve this problem by mapping the marginal distributions. We're going to make a transformation of the temperature values and a transformation of the ozone values independently, but using a carefully engineered change. So the first thing we're going to do is, once again, we're going to pick a distribution that we think is appropriate for the variable. In these cases, I might have picked normal for temperature and gamma for this, but as I told you, I'm going to use this very general solution. And so I'm just going to say, I don't know, just use this, the bounded normal rank histogram. And the first transformation I'm going to do is something called a probability integral transform. What it really is I'm just going to compute the quantile of each one of the ensembles in this distribution. Okay, so that's what I did before. So one near the bottom will have a low quantile. There'll be 0.01. Ones near the top will be close to 1. And this mapping actually changes us to a space where the domain is uniform on 0, 1. That's a fundamental theorem of probability, if we've picked the right distribution. Okay. Then we're going to make a second mapping. And by the way, those of you who know machine learning, although this stuff was actually used widely in data assimilation well back, it is now also used widely in recent years in machine learning things. We're going to do an additional transformation. It's a probit transform. The probit is actually the inverse of the CDF, the cumulative distribution function, of the standard normal distribution. It takes you from quantiles of the normal distribution to values. If that went past you, don't worry about it. The bottom line is once you apply this, the marginals will be normal 0, 1. So the distribution of temperature will be normal 0, 1. The distribution of ozone will be normal 0, 1. When you do a regression in that space, there's a lot of nice features that were not available when you had a possibly nonlinear, bounded, other difficult types of relationships. And so the regression is done in this space. Those two transforms are then inverted. And here's what you get in this particular case. The cyan now is the result of doing the linear regression with these transformations. Again, you can compare to regular regression. You can see that distinct improvement. Okay, so Dart now provides a general capability to pick whatever distributions you want here and do these transformations before you do the regression. And I said I have math given the time. There is actually math behind this. I don't like math. Okay? If you want to look at the slides, or if you want to ask me for the slides, you can see the math. It's in the paper too. There's one more piece that's really interesting, and that is mixed distribution. So what's a mixed distribution? An example is forecast of precipitation for this afternoon. Better do tomorrow because I think we're all 0 for this afternoon. So tomorrow afternoon, there may be a 20% chance that we're going to have some non-zero precipitation, but 80% chance that it's just 0. So that value of 0 is special. It's discrete. And so it does not have a continuous PDF. It just has 0.8 probability there. The rest of the distribution is not discrete. It's continuous. And so it has a PDF associated with it that says, you know, there's a non-zero probability of other amounts of precipitation, but they're all infinitesimal in the sense that any given probability has no chance to really be what is observed. So this can be quite important for some tracers where they may go to 0 and we want a certain number of ensemble members to be 0 while others are non-zero. Again, as I said, it's even more important for sources, anthropogenic sources, wildfires. I'm very interested in these things where the source can go all the way. I don't know that ACOM has done much of it. I'm also really interested in this threat stuff where you might have someone intentionally releasing stuff where it's almost always 0, say sarin, but there's a small probability that it's non-zero. Okay, and again, we have a paper in press that describes how to do this stuff. So I'm going to quickly show you examples in a model we've developed to test this stuff for tracer concentrations and sources. Some of you may be familiar with Ed Lorenz's developments of chaotic dynamical systems. Back in 1963, that got a lot of press on proving that weather has sort of got limited predictability timescales. He developed many of these, and one of these is referred to as Lorenz 96. In its most common form, it has a one-dimensional cyclic array. You can think of it as a set of points around a latitude circle, and it's often used with 40 points. And so you can see those 40 locations, points around a latitude circle at the bottom, the horizontal axis. The vertical axis is time, and so this model is chaotic, and so you can see these things happen. There's obviously some order in there. You can see a group velocity and a phase velocity in time on these values. And so that left panel is what we would call a Hofmahler plot in atmospheric science of this Lorenz 96 model. Now what we're going to do now is treat that Lorenz 96 model state variable as a wind. And we're going to let that wind blow around the tracer on this same 40-dimensional domain, so around the latitude circle, if you will, and that's shown in the right panel. And in this case, I have a single source at grid point 1, shown by the smokestack there. And so we're puffing in tracer there, and then this chaotic simulated wind at the left is advecting that around. And you can see that it does things that are not, there's some physical ideas here. Most of the time, the wind is positive, and so you can see plumes blowing off to the right. Sometimes the wind reverses. You can see plumes blowing off to the left. In addition to the advection in the source, there's also a couple of sinks occurring in here. So there's basically the equivalent of a rainout sink and a chemical conversion sink. The way those are implemented for this specific example, the concentration can actually go all the way to 0 as you get further away from the source. And so the white areas are really 0. And I've highlighted 2 grid points here with the red things. One is a little bit downstream of the source, and one is a little bit upstream of the source. And I'm going to show you some results now for doing simulated data assimilation with this system. So in particular, I'm going to observe the state, the wind basically, occasionally, and I'm going to observe the concentration occasionally with pretty noisy observations. So I'm going to take the value the model gives me in something I'll call a truth run, and then I'm going to add on some noise to that to simulate real observations. And then I'm going to simulate this with these methods we have. So these results are using the traditional methods of fitting a normal distribution and doing linear regression. The grid point 14, the one to the left is at the top. The one to the bottom is the grid point that's just a little bit upstream. The blue line is the actual true value, so we're using one run of this model as the truth. And so you can see the blue showing occasional puffs of tracer reaching both of these points. The green are 80 members from an ensemble assimilation where we're trying to estimate this stuff, and the ensemble mean of those 80 is shown in red. And so with the traditional methods, they work. Okay, so there's a relationship between these tracer fields in the model and the assimilation stuff. But it's long been known that there's problems with bias and other things with these normal methods. And you can see that the green is generally too high, and so there's more tracer. It's getting the shapes of the plumes right most of the time, although sometimes it gets some plumes that don't really exist. Sometimes it still does this crazy stuff, so you can see down in the bottom there's times where there's green going down, so there's ensemble members that are negative there. The next slide is going to switch to exactly the same observations from the same model, and it's going to apply these new methods. Okay, and so here's what you get. The first thing is that the axis changed because there's no negative values anymore. Okay, so the bottom axis is 0. So everything is positive as it should be. There's now much greater correspondence between these things, so the green curves are closer. There's still uncertainty, right? These are not perfect observations. It's a chaotic model, so you don't expect to get exactly the right thing, but you would like to get things that are consistent in the sense I'll talk about in a moment. So these things are much, much better. No negative values. The other important thing is, as I pointed out, these methods now can go to multiple values of 0, or even all ensemble members being 0. And in this particular case, there are some times where all 80 ensemble members have a value of 0 at grid point 36 for the tracer. Basically, your assimilation is saying, I'm really, really sure that there's no tracer here right now. This is another plot showing these differences. Do not worry about the details of the colors of the curves, but this is again across the 40 grid points going around the latitude circle as the horizontal axis. RMSE from the ensemble mean of the assimilation is plotted, and basically the two lower curves in whatever colors those are, I think I said dark blue and green in the text, those are from examples of the new method. One of them uses the new method for both the wind and the tracer. One of them only uses it for the tracer and uses normal for the winds. The other two are cases where you're not using the new distributions for the tracer. And so pretty much across the domain, the RMSE is smaller. The left panel is for an ensemble size of 20, so cheap. The right panel is for an ensemble size of 80, which is what we often recommend to large model users. You can see the improvement of these methods gets bigger as you go to larger ensembles. And that's a behavior that we understand at this point. This slide, there's not many data assimilation aficionados in the live audience. But what I will tell you is this is something called rank histograms. It is a different statistical oddity that shares a name with the distribution I'm using here. Basically, it tells you if a plot like this is uniform, it tells you that your ensemble looks like a random sample from the truth. In other words, you can make conclusions like the following. If 1/4 of my ensemble members are greater than 10, the probability that the actual thing will be greater than 10 is 1/4. You need a uniform one of these to make that happen. The left one is from the old methods, and it's highly skewed. That very, very high peak on the left is saying that most of the time, the truth is smaller than the smallest ensemble member, and you may remember that from the time series. The one on the right is showing you that we're doing a much, much better job. There's still some deficiencies, so you can see a spike at the outermost bins that says that the truth is more often bigger than all the ensemble members or less than all the ensemble members than it should be, but it's definitely much better. Okay, now, this is the piece that I've really been trying to get for years on this, and this is why I came to give you a seminar. All that other stuff is nice. It's incremental improvements. But I think we have something more than an incremental improvement for source estimation. So in this case, again, in this idealized case, now in the previous examples, I said I know what the source is. It's some units where the smokestack is, and it's 0, whatever else when I did the assimilation. But now I'm going to say I have no idea when I start what the source is. And so I'm going to put, these are log scales for error. I start out with orders of magnitude uncertainty and what the sources are at each point. This is using the traditional methods here. The left plot is for the grid point where the smokestack is, so there's really stuff coming out here. The right is for a grid point where there's nothing on the other side of the domain. And you can see that these things, we've known a long time how to do source estimation with these basic methods. And so these things converge, so you lose the ensemble spread, and that's a problem that we know how to deal with. And they have a certain amount of error. Again, this is a log scale of the root mean square error for the source estimation at these points. I'm now going to change the panel, and you'll see what happens if you change to the new methods. So the first thing is you go down by about 5 orders of magnitude on the error on the left panel. That's for the place where you're really pumping stuff into the atmosphere. So you get much more accurate estimates. And the really cool one is the right one is this estimation for the place where there's no source. And what actually happens here is that there's enough information from the fact that plumes are not getting there very often and never appear for the data assimilation algorithm to say, you know what? The more I look at this, the more I see observations as time goes by, I become more and more certain there's no source here right now. And in fact, the estimates will go formally to 0 if you do this long enough in this case where there really is over all time no source. So these are big improvements over what the traditional methods could do. Now, I want to flip it back to a minute. So as a data assimilation scientist, I spend an awful lot of time looking at plots from Lorenz models with 40 variables. And I estimate at this point that I have run trillions of data assimilation steps in those models. And you know what? You guys don't care at all. So the real step towards collaboration is taking enhanced data assimilation capabilities and finding science collaborators, understanding their needs, and giving them tools that work better. And so this is an example that we are actually at that point with these new methods. So this is back to Ben's global CAM-Chem 1 degree assimilating Chris and Moppet. What's plotted here, so this is a 1-month time series of the global fit to these observations. And so the horizontal axis is time. The curve that's of most importance to you is the dashed dotted one. The top row is at 500 hectopascals. The bottom is at 700 hectopascals. These are a single column retrieval. And so Ben is dealing with the difficulties of taking that single retrieval value and spreading them out through the column. I'll mention again, Arthur's research tries to help with that problem. But the key point here is the top curve, the dashed dotted one at 500 and 700 down here, at all times, all 30 days in this example, the RMSE has been reduced by using these new methods for the tracer concentration here. Sometimes people lose track of the fact we don't know what the lower bound on this RMSE is, but it's nowhere close to 0. And so these are significant improvements. To give another reflection of that, you saw this figure before, and we'll come back to it. So there are 4 different examples of data assimilation over there compared to a non-data assimilation control. And so, sorry, there's 3 examples of data assimilation and a non-data assimilation control. Panel A is no data assimilation. When Ben assimilates Moppet, he reduces the RMSE for the global field from 23.47 to 14.66. So having some observations of CO makes a big, big deal. When he adds in Chris, that's the panel C down in the lower left, that RMSE goes down by about 1 to 13.5. And so that's a whole new set of observations. By the way, there's lots of scientific challenges for both modelers and observationalists in combining these observations, because not only does the model have its own idea of where the thing is, sorry observationalists, your instruments aren't all perfect either. And so the Moppet and Chris instruments are actually disagreeing in some places in where they want to drag the model for Ben. But nevertheless, he adds in Chris, he gets better. If he then repeats this, that's in the lower right panel. The lower right panel uses all these new algorithms. Okay, this bounded normal rank histogram for everything. It runs, this was cool because we had not done lots of large model stuff when he started. It ran out of the box with no problems, so no crashes, no need for tuning, no anything else. It runs on, these were done on Cheyenne. We're transitioning him to derecho soon. The total additional cost was less than 10%, so these things are affordable. And you bring down the error again by about another 1. Is that a big difference? For mid-tropospheric tracers, it is what it is. Mid-tropospheric free tracers are not going to have nearly as much impact as if you get in the boundary layer where things have big variability, where observations are there, and especially, again, for sources. I'm not going to show you results. Ben has also been estimating sources. That work is still underway, but it is working there too. So I did want to leave some time for questions, and if people don't have them, everyone can get to lunch early. But closing thoughts here. We're at NCAR for a reason. Tim Killeen brought us here 2 decades ago to provide data assimilation tools as a crucial part of NCAR science, and that's what we do. That hasn't changed, so I think all of you have read the current strategic plan, and I think we know where the next strategic plan is going. So prediction and predictability are key parts of what the organization is doing. And a key tool in the modern world for doing prediction and predictability is Ensemble data assimilation, because we provide the capability to look at distributions, to understand and quantify uncertainty, to evaluate the probabilistic impact of the work that we do. Okay? And the fact that we also need these tools to make our models better by using observations. Making models better is super hard. Okay? People at ECMWF have huge teams that do this stuff, right? We're never going to have a huge team for CAM-Chem, and so we need to use the best tools we can possibly get to do it effectively. Chemical assimilation, as I pointed out a little bit here, and I could give a whole nother talk on why it's such a cool problem for data assimilation and why it's so hard. Bounded quantities are clearly an issue, okay? And we've been walking circles around that for 20 years, and there are better ways to do it now. It also turns out that there's a lot more nonlinearity in a lot of chemical processes than there is in just advecting temperature across the mid-troposphere. And so advection of chemical species, which can have a number of interesting gradients from various reasons, and gradients and other things that come from chemical processes themselves, lead to much more troubling data assimilation situations, and these new methods can help that. I think the fact that Ben saw this just consistent improvement in the mid-tropospheric CO is telling us that even for something that should be pretty normal, that in chemical stuff, there's still lots of cool stuff to do here. So DART, okay, there's a lot of other Ensemble data assimilation tools out there. None of them as general or as powerful as DART. There's a lot of other data assimilation tools out there that aren't Ensemble. They can do great things, but they can't give you uncertainty quantification. So DART has unique capabilities, especially these new methods that are relevant to chemical applications. And DART is available for all your NCAR models right now, and we're going to continue to support and hopefully continue to collaborate with you on applications in those models. So as I said, I'm down here giving this seminar because, like I said, none of you care what we do with low-order models, and NCAR doesn't really either. At the end of the day, we're all earth scientists who happen to do data assimilation, but the biggest win is seeing some application where you say, we made important science better. And so we're really, really interested in finding ways to increase our current collaborations and really look for some new collaborations. And again, I think modelers are already aware that they can collaborate with us. They just have to find the time and the incentive. But I think one of the final takeaway message I want is observationalists, I think we can really provide some stuff that will enhance the impact of your atmospheric chemistry observations, and we'd love to talk more about that. So thanks, especially those of you who showed up in person, but thanks to everyone watching online or recorded too.
We have time for questions, and for people watching online, please enter a question using the Slido. So we'll start with, in the room.
Hi, Jeff. Thanks for the great talk. So I wonder, so the new features you mentioned, the non-normal distribution, is that available now in DART?
Yeah, so DART is under full version control and is community development. The DART main release right now does not include these things, but we have a branch release that we're putting out to beta users. So obviously, Ben is using that. Arthur Mitzi has it. Ave Arellano, who some of you may know, is using it down at Arizona. And if you're interested, we would be happy to give you the pointer to that and talk with you. The documentation on the new thing is not as comprehensive as the old, but it is also documented. So if you're interested, whenever you'd like to try it out, contact us at either me personally or dart@ucar.edu, and we'll get you a chance to look at it.
Thanks. So it has been being tested now with 3D models?
Yeah, so I mean, Ben's work is in CAM-Chem Global. Those are 1 month CAM-Chem Global 1-degree integrations. So, but we've also tested, we've tested in ocean models, so POP. We've tested in WRF-Chem. We've tested in plain old CAM. So it has been fairly comprehensively tested. Encouragingly, as an aside, we worked with a much more rigorous numerical software development process on this than we have on anything else. And so when we rolled this out, we have not found so far, it's been out for friendly users on some stuff for almost a year. We released it at AMS last year. And we have not found any fundamental algorithmic bugs so far. And we have not had applications where it has crashed where the traditional methods run. In other words, if your traditional normal methods are running, so far this has been running out of the box. That could change. I don't want to mislead people, but so far this has been by far our most robust software algorithmic rollout in the 20 years we've been doing this.
Thanks.
Helen.
So I had a sort of out-of-the-box question of, do you have any plans to combine ensemble results with machine learning so that you could do prediction of both mean and spread using machine learning and not have to run the whole ensemble every time?
Yeah, so a great question. The boundaries between AI, machine learning, and everything else we do at NCAR are fluid and interesting. So I spend a lot of time sitting with our Miles group, which is great, by the way, for those who don't know that, David, John, and the folks there, sitting in CISL, but they are really collaborative. So I would suggest talking with them about that too. But that being said, first, the biggest of big data is what we do, right? So we roll out ensemble analyses and forecasts, not only of the model, but also of the observations. And so Ensemble DA is the biggest big data problem in geosciences. And so that's what ML is all about, right? And so your question about could one apply stuff to do things about the uncertainty, my understanding is absolutely yes. It's a really big problem, and I am not going to say anything about the technical things of that. There are experts around doing that. There are also other really useful things at the boundary between data assimilation and machine learning. So data assimilation has a long history of looking, and I didn't mention it here today. I basically told you on the model side, I can give you tools that basically you don't have to know anything, for better or worse. The observation side, that's still not true. And so I said, well, you have to tell me the distribution and whatever else. But in fact, there are methods to estimate using big data on the observations and their comparison stuff also. And in fact, Henry, sitting back here, Henry Sandra, visiting from University of Maryland right now, has been implementing some more traditional methods for doing that in DART during the past few months. One could also do that with more sophisticated machine learning techniques to say what really are the errors with these observations. And so I think there is a huge area of growth cleaning up observations and stuff like that. The other thing, of course, is many of you are already aware that people are building machine learning inspired and developed emulators for large models. Again, there are pros and cons to doing that, but the one thing it lets you do is get pretty good model estimates in vast numbers. Those vast numbers of things we could actually ingest, and we know that these ensemble methods continue to get better as you move to larger ensemble sizes. Those ensemble sizes have always been limited by this tension between how big a model can I use versus how many ensemble members I can run on a machine. If you change that dynamic, we are watching closely, but the potential to run these types of algorithms with 1,000 members instead of 80 in a large model, I know that there's huge improvements between those things. And so there's all kinds of fascinating potential at that boundary there moving forward. So it's a great question. Did I actually answer it, by the way?
Yeah, no.
Okay.
I mean, I'm going to think of more specific problems like estimating emissions with errors, which is something that you can't really do very well with other data assimilation methods. So.
Yeah, so to come back on the machine learning. So recently, I think it was a couple of weeks ago, I think it was Google who made this weather forecast, without using, anything normal except machine learning and AI. So how do you see that development compared to, how will this balance change between data assimilation and that type of techniques? Because you can also start to do that for air quality, but we have probably a more nonlinear system. So what is your expectation there?
Yeah, so first of all, I'm going to caveat with, now you're going to get my opinion, and we're far enough from my area of expertise that you should question my opinion even more than you do when I'm talking about stuff I know about. But I'm going to answer some things anyway. And because I think there's important dynamics here that we cannot lose sight of as a community. And that is that machine learning is designed to take a set of predictors and a set of predictands and come up with a way to estimate the predictands from the predictors. That's what we do for forecasting. So clearly at some point, these are the same problem. Now, in the ultimate end game, you would take your observations and you would feed those into machine learning, and you would have those at one time as predictors and another time as predictands. And you could do that. Now the problem is there that the only thing you can predict are the things you're observing in that case. And so there's immediately a need for some sort of model somehow to get you to things that are not observed that you still care about predicting. And so we can't lose track of that. There's this idea that you just get rid of models, that you get rid of everything, and this is happy world of predicting is conceivable with enough data and the right tools, but it's not the question that people want. And so that brings you back to the models. And as I said, EC, I don't care what Google does. I care a lot more about what ECMWF does because I trust them. So ECMWF has shown that they can emulate their big current model pretty darn well and make forecasts. So there's so one thing to remember there is that the machine learning will not make it better. If you train it off the current model, you're done. Okay? It's not going to get better. There's not going to be improvements in the forecast. We're going to be here forever. And so for now, the only path forward on that is to continue the development of the model, and maybe you only run it to train the machine learning, okay, and you get a computational saving there. But it's not like you can send the model developers home if you want to follow this 60-year period of incremental improvement to NWP. Similarly, I'm almost done, on the observation side, okay, is that the things we're doing with data assimilation are also adding value that is not immediately available from just mining the observation. You have to somehow know how to get those observations to the model, and that's not observed. And so somehow or other you have to have a independently inspired process to do there. And for now, my feeling is that neither the model nor the data assimilation go away. We keep making them better and better, but it's possible that no one will ever run them outside of a training period.
Yeah, but you might think about a combination of those two techniques, so the data assimilation, and because the speed, you know, that is a problem with DART, I would say, to do that for chemical species, that the speed is an issue in the end.
Absolutely. So I agree with you there. I think the point is that you have to train off that. And I already went halfway there for you in the earlier question, and that was, if you'll give me a 1,000-member ensemble that's not quite as good as would come from running 1,000 copies of the real model, or maybe almost indistinguishable potentially, I can do a lot with that too. But you're right, in the long run, if you can emulate that process also and make it much more expensive, why wouldn't you? But you have to remember that you can't throw out the other stuff unless you want it to be the end of the era.
Yeah.
Okay. I think just now, Abby, want to wish you a safe travel. I think that question was gone. Yeah.
Yeah. So I'll take this question on the bounds. So in fact, you do have to tell the methods that there's a bound, and it is possible to bound both below and above at arbitrary values. But you do have to specify that, and so normally that type of knowledge is something that you really, really do know. Okay, it's ozone concentration, it's bounded below. We've done examples of sea ice aerial coverage or snow aerial coverage where it's bounded below at 0, bounded above at 1. And so both of these can be done. I actually have a test suite that does bounded above 2. I haven't actually come up with any applications, but it's numerically challenging. It turns out it's much harder to do bounded above at a non-zero value with standard numerical models than it is otherwise. So,
Okay, maybe one more question and then, yeah, okay. Biru asks, thank you for the great talk. Have you investigated whether this new technique also helps improve long-term, for example, 1 month forecast as it improves the initial condition?
Yeah, and the answer there is quick and easy. We have not done any extended forecasts yet. We know that there are people in CGD, amongst other places, that are interested in this, and we are working on building collaborations to take a look at this stuff, but nothing's happened yet.
Okay. Thank you, everyone. Yeah, have a safe commute, Jeff. We'll see you next time.